There we go. Now we're going. Hello, Algebra 2 kids. Hopefully this goes well for you and you're doing well. And please let me know whatever questions you have. If there's anything I can do to help make this better for you, and hopefully you can take time to rewatch this or pause it, stop it, go back and listen again. I'm going to try to go fairly quick so it doesn't drag out too long. I'd love to have you in class for this lesson. A lot of stuff we talk about, a lot of application that we have with this next section that we're going into. So one thing is that if you have an immediate question, if you're working on something and you're just stuck, you know you don't have a right answer, you're not sure what you did wrong, if you want to, you can shoot me a message or an email. My phone number is on your assignment sheet on the back on the resources and tips on that last tab. But take a picture of the problem and what you've done so far, and then I can troubleshoot with you what it is, what you need to do. But that is kind of the main thing to get going with a problem. So if you're in the middle of something, you want to figure it out, just make sure I know what you've done and what the problem is, and I can respond pretty quickly. Hey, try this. If you're kind of clueless with a lot of things, you have a lot of questions, let's wait till our classroom time, which our first one will be Tuesday around 10:30. And you should have an invite to that in your email box. Please be checking that regularly. Do not expect a full instruction when we meet. You need to watch these videos and go over that at that time. I want to review anything that you need to review over or answer any questions at that time, but I wasn't trying to do a whole lot of new teaching with that. So that's what these videos are for. As we go through these, have your student journal handy. Please be writing stuff down. Do not just watch and be like, yep, I know. You write it down. You need to write it down. It's going to help you learn. This is going to help you remember. You have to do more than just sit at the computer screen and try to soak it all in. Whenever you write stuff down, your brain remembers things better and you'll learn better. So be writing stuff down as I am. You can pause it, figure things out ahead of me. Don't just watch me do it. Stop it, and then work problems ahead of me. See if you can figure it out, then come back and watch, see how I did it and what answers I got. I have also uploaded all the answers to the student journal in the Google folder that I shared with you as well. So let's get going. I try to keep these, I want them under 15 minutes, but a lot of them have been 15 to 20, and some of the upper level ones might even be longer. But I will try to condense it, keep it as short as I can with still getting the information to you. So what we're looking at here is this right here, and if you've paid any attention lately, the term exponential should be pretty common to you. An exponential function, things that are growing exponentially, if you've heard that. That's what these functions right here look for. So this might look familiar if you've seen any charts. We're going to look at some here in a little bit. So these right here, this would be an exponential growth, something that starts low and it grows just really slow over time, and then it, boom, zooms off. This has a common scale factor, means you're multiplying by something every time. So there's an old story, if you had a job for a month, would you rather get paid a penny the first day and it doubles every day, or would you rather get paid and that's how much money you get that day, or would you rather just get paid $10,000 a day for every day for 30 days? So the first way ends up being a lot more because at the beginning it's very low, just a penny, then 2 pennies, then 4 pennies, 8 pennies, 16 pennies. But by the end you're getting millions of dollars every day. Okay? So that ends up being a lot more than just $10,000 a day, or even $100,000 a day. So exponential growth, this is going to be called exponential decay when a graph looks like this. Okay, so these are some of the charts. This is the U.S. We can go look at some other countries as well. Okay, this was yesterday's numbers. I think those might be today's, but a lot of these, because it was complete. And if I scroll down, look at that. There's your exponential growth. So you notice we were pretty quiet, and then right before spring break, that's when numbers started going up, and now all of a sudden people are freaking out because they just saw that little bit of growth. They knew what could happen after that. Okay? Now, I don't want to put fear or anything in you. A lot of these numbers represent what's happened in the past because things take time to develop. But this is the daily new cases in the U.S. Okay, how many are confirmed each day? Active cases, exponential growth. So when they're saying flattening that curve, they're trying to flatten that out so it doesn't grow as exponentially anymore. This would be the total deaths, not the deaths per day, but the total deaths. But the daily deaths are going up right now as well. So exponentially, you notice here as we go from day to day, it's not going up each month very much. But it's a percentage. So if you take 20% of 50, that's not very much. It's going to just be 10. But if you take 20% of 54,000, that's going to be a lot higher. That's going to be over 10,000. So you notice here now it's jumping. It's going to probably be about the same percentage rate on an average, but when you have much larger numbers, your percentage is going to be a lot higher. Okay. So I've enjoyed looking at the charts and the cases and things that are happening with the numbers, but I do not do it as a fear factor. Congratulations, U.S. If we go to today's, waiting. Why this one's going to take longer. The U.S. did exceed China, if we have accurate numbers from China. Okay, so congratulations, Ikram, you're not in the top 2 anymore. So we can go look at what's happening in Italy as well. Okay, so you see that right there. We've been increasing, and starting about May 22. They're still going up, but it's not so much exponentially. We may call that a linear graph right now. It's a line. So that's a good thing. We want to start seeing that flattening out. So I think you're going to continue to see good things happen back there. Ikram, you'll be okay. Here's your daily new cases. See how it's been dropping. Okay, so that doesn't mean everything's fine, hunky-dory. Go outside and start being as active as you were before, but things are getting better. People need to continue doing what they're doing. So that's good news for you, Ikram. I hope you're seeing that and saying, hey, things are improving. Things will be getting better. So, exponential growth and decay. Your main formulas. Let's get rolling here. The main thing with an exponential function, okay, an exponential function has to have a variable in the exponent. Okay, so an exponential function is when the independent variable is in the exponent. Independent variable is the x. Okay? So when it's in the exponent, that's when you have an exponential function. Okay? So if you have an x squared, that is not an exponential function. It's a quadratic, that's a polynomial function. It is not exponential because you have a 2 in the exponent. But if I have 2 to the x, that is exponential. Okay? So some of your first questions are just going to ask you to evaluate the functions at certain points. Okay, so evaluate 4 to the x for x equals -2 and x equals 3. So you're just going to put the -2 for the x. You can use your calculator to help you with that. You don't have to, because a lot of these you can do in your head, but some of them may get trickier as well. So feel free to use that calculator. I know a lot of you already are. Okay, so that's what the first part is just plugging in the number for the x and calculating it. Remember, those are exponents, not multiplications. Okay, there we go. So this is an exponential growth. The main thing here is when you have b to the x and b is greater than 1. That's how you know it's an exponential growth factor. So something like y equals 2 to the x, y equals 1.1 to the x, y equals 5 to the x. Those would all be examples of exponential growth because 2 1.1, and 5, all three of those are greater than 1. So B has to be greater than 1 for the exponential growth factor. So when you have questions asking whether something is a growth or decay, you have to look at what your base number is. The other equation here, or domain is going to be all real numbers. It goes forever left, and it goes forever to the right. It's pointing up, but it does go forever to the right. Time keeps on going. The range is y is greater than 0. So you can only have positive answers. Now, if you have some sort of graph transformation that moves the graph down, you can get negatives that way. But your standard graph is always going to be positive answers. This right here, this term right here, this is an asymptote, is a line that a graph approaches more and more closely, but it's never actually going to touch. That is what the x-axis is. So as it goes forever to the left, it's going to get closer and closer to the x-axis, but it's never going to touch it. One hint is I'm not going to take time to fill in all these vocab words, but I highly encourage you, as you read them down below, is to come back and fill in different parts of it and write it out. Okay? Record it, write it down. The other thing is an exponential growth equation, which is a model. So if they're talking about modeling things, you need an exponential growth equation. That is this one. Y equals a times 1 plus r to the t. We saw this in Algebra 1. Y is the final amount of what you're having. A is the initial amount. So if you start with $500, you'd put 500 there. R is your growth rate as a decimal. So remember, if you have 2% growth rate, if R equals 2%, you're going to use 0.02. So if R is 2%, you use 0.02. If you have something like 0.75%, which a lot of savings accounts use, you have 0.0075. That is the value you would use. So you make sure R is a decimal. T is time. This parenthesis is referred to as the growth factor. So don't confuse the growth factor with the growth rate. R is the growth rate. This 1 plus R is the growth factor. Okay? Exponential, we'd have a ton of discussion if you're here in class about savings accounts and investments and loans, and all of those play into exponential growth and decay. So that exponential graph we saw, your goal as you go through life and your savings for retirement, stuff like that, is to get an exponential growth. So right now, even me, I'm investing and saving. It doesn't look like it's going up very much, but my goal is eventually when I get closer to retirement age, I'm going to hit that peak and it's going to be exploding up. That's the goal, at least. Okay, I don't need that page. This one's exponential decay. So this is your decay. It's going down. This is when the b is between 0 and 1. So the graph is falling. So the graph is getting smaller and smaller. This is what they call depreciation. So you buy a new vehicle or a farm implement or something that depreciates, it loses value. So something like y equals 0.8 to the x. Y equals 0.4 to the x. Y equals 1/2 to the x. Okay, all of those would be exponential decays because your b value, your base, is between 0 and 1. Okay, domain is again all real numbers. The range is greater than 0. Okay, it never goes negative. Now if you'd have something like y equals 1/2 x and then you have minus 10 at the end, that's a graph transformation moving it down 10, you could essentially end up with y values. Then your range would be y is greater than 10 because you had to move the graph 10 down. Your decay equation is the same thing, except the only thing that's different is the minus sign because you're losing value. So that is called your decay factor. Now what I talk about, if they have R is 10%, let's say R is 10%, again you'd use 0.1. Let's say you have a 10% off sale. So if I do 1 minus 0.1, I get 0.9. That would be my decay factor. So if you get 10% off, remember everything has to always add up to 100. So if you have 10% off, you'd be 90% on. So you're paying 90%. So 10% off means you're paying 90%. That's your decay factor. The third formula is called compound interest. This is when you earn interest on your interest. And this is what is used on savings accounts. Okay, and loans that use compound interest formulas. You can figure out if you invest Or save money, say $500 at 2%, how much will you have after 5 years if it's compounded monthly, which is very similar. So this is a formula. It looks very similar to what we've had. This A is your final amount. The P is your starting amount. And all this is up here. P is the principal. It's what's deposited. R is your annual rate, expressed as a decimal, compounded n times per year. So if you have something that's compounded monthly, that means n is 12. So they're going to take your percentage rate and they're going to divide it by 12. But they give it to you 12 times more often because it's 12 times t. So there's an n times t up there, there's an r over n right here. So compounded monthly means you take your percentage rate, they divide it by n. So let's say we had that. We had $500 invested at 2% compounded monthly for 3 years. How much would we have after that? So our amount would be the principal, how much we started with, $500, times 1 plus our rate as a decimal, so 2% would be 0.02. We're going to split that. That is an annual percentage rate, so over a year you get that. We're going to split that up between 12 installments. But then we have to figure it out every month, so we're going to take it times 12 times t, which is 3. So 12 times 3. Make sure that's in your calculator. Okay? So, and all of this can go in your calculator, but you have to make sure you hit the right key sequence. So 500 times 1 plus 0.02 divided by 12. You can leave that as it is. The calculator will do the division before it does the 1 plus 1. Now here's the key part. When you do an exponent, you have to use a parenthesis or do this multiplication in your head. Okay, that'd be 36. But if you hit it just raise to the 12th then times 3, it'll raise this to the 12th and take your answer times 3. So we get $530.89. So after those 3 years, you gained $30. Okay, so those three formulas, good to know: compound interest, exponential decay, and exponential growth. Okay, so your questions, you have the plug-in ones. The next sets, they ask you whether the function is a growth or decay, and then to identify the graph of the function. Okay, so tell whether the function x represents exponential growth or exponential decay. You're looking for the b value. Growth is if b is greater, your base value is greater than 1. Decay is if it's between 0 and 1. So look at this one. Sorry, there we go. B is between 0 and 1. Y equals 1/12 to the x. That's my b value. Well, 1/12 is between 0 and 1, so that has to be a decay. We'll talk about graphing here in a little bit. Y equals 1.5 to the x. Well, 1.5 is greater than 1, so that has to be a growth. Y equals 7/2 to the x. It's a fraction, but 7/2 is greater than 1, so that is a growth. 0.8. 0.8 is between 0 and 1, so that is decay. All right. And to help you with the graphing, we will utilize Desmos. So y equals 1/12 raised to the x. Oops. Okay, so there's your decay. Oh, zoom in. Okay, so you can get some points here. 0, 1. You can find some other points here to help you graph it. Okay. 0, 1 is going to be your y-intercept for all of these, because anything to the 0 power should equal 1. You can find some other points. Looks like -1 is way up here somewhere. 12. Yep. 1/12 to -1 would be 12. Okay, so you can use Desmos to help you graph it, get the picture of what you need. Okay, next set, so that's those questions. State whether it's exponential growth or decay, and then select the graph. Okay, this is when you get into the models. Okay, let's go back to Student Journal. So here we have the number of bacteria in thousands. That's important. In a culture can be approximated by this model here. So this is the starting amount. And then this is a growth because it's greater than 1, where T is the number of hours a culture is incubated. Tell whether the model represents exponential growth or exponential decay. We know this is a growth because 1.99 is greater than 1. Identify. Hey, Mr. Hoops. Want to come say hi? Again? This is a different class this time.
Oh, is it?
Yeah, this is Algebra 2.
Oh,
Yeah, you talked to, Tate, Rachel.
All right, yes. Good job. Keep working, kids.
I know.
I really love it.
I'm sure they are. Okay, so this is a growth. 1.99 is greater than 1, so it's growth. The hourly percent increase or decrease. Well, we know it's an increase because it's a growth in the number of bacteria. Percent increase. Okay, now 1.99 is the growth factor. It's not the growth rate. So remember, 1 plus R has to equal 1.99. So if you have a growth, you want to take 1.99, take the growth factor, subtract the 1 off, and you get 0.99. That means you have a 99% growth factor, percent increase. Okay. So let's say you had something like 0.8. So let's say we had the 100 times 0.8 to the T. That's a decay. What is the decay rate? Well, if you take 1 minus 0.8, you get 0.2. That'd be a 20% decrease. Okay, so that's how you do those if you need the rates. Okay, remember, the rate is not 0.8, it's 1 minus 0.8. Okay, and on an increase, take the growth factor minus the 1, and that's you get what your increase is. Estimate when the number of bacteria will be 1 million. So they want to know when will our formula equal 1 million. Okay, and again, Desmos is going to be our friend, and this is going to be a big graph. So I'm going to type in my function. I have 100 times 1.99 raised to the, now don't use T, use X, okay? And then I also want to know, okay, when does Y equal 1 million? Okay, so I got to zoom out a ways here. Zooming is an exponential function. Notice it took a while, now all of a sudden we're getting lots of numbers here. Oh, that's 100,000. Not there yet. There it is. Okay, 13.385 and 1 million. So T would equal 13 point... Oh, wait. That's not right. Sorry. Remember, the number of bacteria is in thousands. Okay, it is in thousands. So when it's a million, that is 1,000 thousands. That is 1,000 thousands. So we got to find out when it's going to be 1,000 because we're not. Yeah, we're not starting with 100. We're starting with 100,000. Okay, got that. So all that zooming was not as needed. Okay, let's do this. Again, you can also just change your settings. There's 1,000. 3.35 hours. Okay. So 3.35 hours. After that, you would have 100 million bacteria. Okay, a couple examples with the compound interest. Then I'll check to see if there's anything else we need. Okay, use the given information to find the amount A in the account earning compound interest after 5 years, that's the T, when the principal is $12.50. Okay, so A equals P times 1 plus R over N to the NT. This is your time to kind of pause this and go try to see if you can get the right answer. Come back and see what I got. So I'm starting with 1250, 1 plus 0.0225 over quarterly. So N is 4, raised to the parentheses 4 times 5 power. So 1250 times 1 plus 0.0225. Let me get this so you can see it. 5 divided by 4 raised to the 20th power. So 1,398 and 40 cents. Round to the 100th. Okay, 1.25 compounded daily. So A equals 1250 times 1 plus 0.0125 divided by 365 raised to the 365 times 5. They're doing it every day. So 1250 times 1 plus 0.0125 divided by 365 raised to the 365 times 5. I won't do that in my head. So 1330 61. Okay, those answers you should get on that. Okay, so I need to be done with this lesson. It's gone way too long. That should give you, yep, there's your compound interest questions. Okay, the other thing is on your assignment page, I'm going to put these links right here. Okay, you should find it here. I'll also email probably this first one to you. But that's where you're going to find the links. I've already done some for geometry. Okay, good luck, kids. Let me know what questions you have, how I can help you, and I'll start working on your next lesson.